So we usually use Dirac notation to describe elements of a Hilbert space. So that is the state psi, which is an element of my Hilbert space. Curly H is my Hilbert space. Now we tend to describe Hilbert spaces by their basis sets. If you've got a complete orthonormal basis for a vector space, you basically know everything about it. So you might have a photon, which would be described by horizontal and vertical polarizations. Or you might have a particle with spin j. And if a particle has spin j, then its projections in the z direction have values of minus j up to j in steps of 1. Or you might have systems that have spatial dependence, in which case they could be at any point in space, and these basis states would take every single value of the real numbers from minus infinity to infinity. Or, of course, more commonly, you have particles that have both spin and spatial dependence, in which case the basis set has values of mj and x. And so every different possible combination of mj and x gives us a new basis vector. And what this means is that, for example, something living in this Hilbert space, an arbitrary state would have to have a different complex number coefficient for each one of these basis states. So we'd have to sum over the mj's, and we'd also have to integrate over the x's. And we'd have a complex number, which depends on mj and the x, and we'd have this basis vector. This is a linear combination of these basis vectors. And this thing here is what we often think of as the wave function, if we're thinking about things with continuous indices. But the wave function and things that have discrete index, they're just the same thing. They're just the coefficients in that basis. Now, for a set of vectors to be part of a complete orthonormal basis, then we have to have an idea of what orthogonal and normalized is, which means we have to talk about inner products and indeed the dual space. And so to go from a vector in the vector space to its dual space, it's quite simple. All we do is we take the complex conjugate of all the coefficients. And you can see we turn the ket into a bra, which is the covector. I want to briefly emphasize the subtle change of units that happen when you go from discrete to continuous indices. If I have two states out of this Hilbert space, and I take the inner product between them, then this is going to give me the delta function because this is a orthonormal basis. However, it's going to be a delta function for the discrete index, mj and nj, and it's going to be a delta function for x and y, which is a continuous index. And we know that we always end up with a Dirac delta for that. However, this has no units, and this has units of inverse length. So in fact, each of these things here must have units of inverse square root length. And if that has inverse square root length, notice that this integral has units of length, and that has inverse square root length, so the coefficients also have inverse square root length. So you might recall that the normalization for a wave function is something like this, or indeed if it had some other index like an mj, we'd have to sum over it. But you'll note that this has units length, and therefore this thing must have units inverse length, and therefore each of these coefficients must have units of inverse square root length. And so continuous indices actually have units in both the basis vectors and the coefficients. Given this is revision, we'll move on quickly. So the next postulate of quantum mechanics is how these states evolve in time, which is governed by the Hamiltonian. Now this is the Schrodinger equation. Note that it's an entirely linear equation. It's linear in this state psi. Now supposing I was to put this into a particular basis, for example, my Hilbert space might be the space of a scalar field, a single dimension scalar field, in which case the basis would be one state for each different possible position. And if I want to put anything into a particular basis, the best way to do that is to use the completeness relation, which relates the identity operator to any set of projectors of a complete orthonormal basis. So for this Hilbert space here, then this is the identity, this set of projectors. If instead we had this kind of space here, then the completeness relation would have been something like that, where once again we have to sum over the complete set of orthonormal basis sets. Now the most efficient basis to solve this equation is in the eigenstates of the Hamiltonian. So let's expand this in terms of the eigenstates of the Hamiltonian. So we use the completeness relation written out in terms of the eigenstate basis of the Hamiltonian in order to replace these identity operators here, where we've defined these EJs thusly. In other words, this is the state, that's the eigenstate, and the eigenvalue is EJ. Now this bracket here, this inner product, is just a number. It's a number that depends on J and it depends on the state. And this is precisely the coefficient of the EJ state. So we could say that, in other words, we can expand our time-dependent state in terms of these time-dependent coefficients, and these coefficients here are exactly this inner product here. And so we can write this out, remembering that the basis vectors themselves don't change in time, And we can apply this linear operator through the sum, and it acts on this, and we know exactly what it does. It just pulls out an eigenvalue. And so we have this equation here. And if we take the inner product on each side with one of these bras, and making very sure not to use j, because that's the one we're summing over, so we have to use a different index. And we have assumed that these are forming an orthonormal basis, and so therefore we've got an orthogonality condition between these things. So this is just the delta function. The inner product between ek and ej is the delta function. And same on the right-hand side. And delta functions are excellent things to have inside sums because they get rid of the sum. So we can do that. And we have a very simple differential equation which we know the solution to. And so if we know how to take the Hamiltonian and break it down into its eigenstates and eigenvalues, and I know how to take my initial state and break it down into some superposition of those eigenstates, then I know my solution for all time. So if this is my initial time for some set of Cj of zeros, then I know exactly what those coefficients are as a function of time. They just, each different eigenstate rotates at a different rate in phase. So here we have the Schrodinger equation, which is an entirely linear equation, and here we have the complete solution. So if we expand it out in terms of the energy eigenstates, here is the exact solution of the coefficients of those eigenstates. Now, because this is a linear equation, we could instead write the solution in terms of a linear operator. Now, if this equation were not linear, we wouldn't necessarily be able to write it in this form. This operator here is called the time evolution operator, and it has a special property, which is that it is unitary. Now I want you to take a moment and see if you can remember the definition of a unitary operator.